So, in the last class we looked at the syntax and the semantics of propositional logic. So, what semantics gives us is that it gives us a mechanism for determining which compound formulas are true and which compound formulas are false essentially. We also saw that there were three kinds of sentences that we talked about, a set of tautologies, a set of contingencies and a set of contradictions. Now, tautologies are of particular interest to us and we are often interested in knowing in whether a certain large formula is always true or not. And the only way to construct to find out using the method that we have seen is by constructing a truth table for all the this thing. So, what does a tautology mean? That for every atomic sentence for every possible valuation, there are two of them, the final formula must be true essentially. Now, if you have two variables, then we saw that we have 4 rows in the truth table essentially. If you have 3 variables, there would be 8 rows. If there were 4 variables, there would be 16 rows. So, the size of the truth table tends to increase exponentially with the number of propositional variables, and therefore, if you are talking of a large problem, it is not always a viable idea to build a truth table essentially. Moreover, when we move to first order logic, which is a more expressive language, we will see that the idea of truth table simply just does not carry over at all essentially. So, logicians have at all times been interested in some other ways of arriving at these formulas which are of interest to us, and the other way that we are talking about is a proof system. So, proof systems are basically a language that we have already defined plus rules of inference. And when we put an algorithm on top of that, then we have a proof procedure essentially. We will come to that eventually. So, let us look at proof systems. So, we started off with a language itself is defined by an alphabet and a set of formulas that you can construct in that language. Then we define the semantics. Now, we are talking about rules of inference. So, what is a rule of inference? It is a syntactic device which allows us to add more formulas and extend the knowledge base. So, proof systems are they do not look at meaning essentially, they do not look at truth values essentially. So, they are not really concerned with truth values, they are simply they just tend to treat the knowledge base as a set essentially, a set of formulas that is given to you, and a proof system allows you to add more and more formulas to this set essentially. And how do we add new formulas? We do that by applying some rules of inference essentially. So, let us start off with some examples of rules of inference. The most common that no doubt you are familiar with is called modus ponens. We will use the term MP. Modus ponens says that if you have a proportional variable p. Remember, it is a variable and you can plug in actually any formula instead of this p. And if you have a formula which uses a proportional variable and another proportional variable q, then you can add q. This is a rule. It is not really concerned with truth values. It simply says that if you can plug in something into p and that same thing into a formula called p implies q, then you can infer or you can add q essentially. We have been used to writing this also as p implies q as and q. It is the same thing, just a different notation for writing these formulas actually. So, basically what this says is that in your knowledge base, if you can spot these two patterns, one corresponds to some formula and the other corresponds to a larger formula where this is the antecedent of a implication. So, whenever we talk of implications, we call this the antecedent, and we call this the consequent. And modus ponens is the most commonly used rule of inference. In fact, it was, if you look at any textbook on logic, you will see that it was known to Stoics. These were people who were in the early Greek times. So, it is a school of philosophers called Stoics, and they had used modus ponens as a rule of inference quite maybe 2000 years ago or whatever, something like that essentially. So, let us look at a couple of more rules of inference. There is another rule called modus tollens, which can be written as if you have not q and p implies q, then you can infer not p. Which we can also write as not q, p implies q, not p. So, let us look at a few more rules. There is a rule which says that if you have p, then you can add anything to it. This rule is called addition. There is another rule which says that if you have p and q, you can extract one part of it. It is called simplification. There is another rule which says that if you have p or q and you have negation of one of them, then you can infer the other essentially. This is called disjunctive syllogism. There are other rules. For example, if you have p implies q and q implies r, then you can infer P implies this is called hypothetical syllogism. So, basically a rule of inference says that you can add new formulas using this particular pattern matching approach essentially. The question that we want to ask is when is a rule sound or valid. When is it okay to add this new formula? What do we mean by that is that if you are looking at a set of true formulas, then a sound rule of inference will only allow you to add formulas which are necessarily true essentially. So, the answer to that is that it must be based on a tautological implication. So, what do we mean by that? So, basically what this means is that it must be based on a true statement and the true statement must be of the form where the main connective is an implication essentially. So, for mode exponents the corresponding tautological implication is P and P implies Q. The whole thing implies Q. So, what we are saying now is that if this statement is a tautology, then the modus ponens rules is a sound rule essentially. So, let us see whether it is a tautology or not. There are a couple of ways of trying to make it to show that it is a tautology. One way is to try to show that it is not a tautology, which means to try to make it false. Now, if you want to make this formula false, you know that if you look at the truth table for implication, you will have to make this true and you will have to make this false essentially. So, if you want to make this true, then you will have to make this true and this second part also true. So, if we are saying that P is true and Q is false, then P implies Q is false by the truth table, because true implies false is false. That is the only case where an implication sign is false and therefore, this is false, this cannot be true and therefore, we cannot make the whole formula false essentially. We could have also constructed the truth table for this. So, let us do that I think. So, we start with P and Q. So, they can be true or false. These are the 4 combinations you always need with 2 variables. Then we have P implies Q. We know that in this case it is true, in this case it is false, in this case it is true and in this case it is true. Then we have I am inserting here this larger formula which is P and P implies Q. which is basically the AND of this one and this one. So, T and T will give me T, T and false will give me false, false and 2 will give me false, and false and 2 will give me false. Now, I am saying that this larger formula, which is the, so let us call this M. So, if we write the truth value of M, so I am saying that this implies this, that is the largest formula, right. P and P implies Q implies Q. So, when this is true and this is true, this is true. When this is false and this is false, this is true. When this is false and this is true, this is true. And when this is false and this is false, this is true. So, this is that M, right. And we have shown that this is a tautology. That this formula will always be true. The last column is always true. So, that is one way we said that we can show something is a tautology. So, we can show that the underlying implication for modus ponens, because what is the modus ponens saying? It is saying that if you have P and if you have P implies Q, then you can add Q to your knowledge base essentially, and this is the underlying implication. And once that is a tautology, we know that it is a sound rule of inference. So, for every such implication statement, you can create a new rule. So, for example, you can as an exercise show that modus tollens is sound. Or any of the rules that we have spoken about. Also, as an exercise, show that this rule Q and P implies Q implies P is not sound. So, you can separate the sound rules from the unsound rules by simply looking at the underlying implication and show that if it happens to be a tautology, then it is sound, otherwise it is not sound. Incidentally, this rule is called abduction. So, even though it is not a sound rule of inference, what do you mean by it is not a sound rule of inference? It says that it is possible that the inputs, the antecedents, which is in this case Q and P implies Q are true, but it is possible that P is false essentially. You can see that Q, whenever supposing Q is true, whatever the formula Q is, and if P is false essentially, then you can see that the left hand side or the antecedents are true. Q is true because we said it is true, and because P is false, P implies Q must be true. So, that is true, but P the consequent is false essentially. So, this is not a valid rule of inference, which means we cannot use it in our proof methods essentially. So, before we move on, we should also look at rules of substitution. Because they are often very handy devices. These are based on tautological equivalences. So, rules of inference say that if the left hand side is given to you, then you can add the right hand side, or if the formulas above the line are given to you, then you can add the formulas below the right. Rules of substitution allow a two-way exchange essentially. You can substitute either formula for any other formula essentially. So, we have already seen some examples of this. For example, we have said that not alpha or beta is equivalent to alpha implies beta. So, based on this we can have a rule of substitution, which says that if you see the left hand side somewhere, you are free to substitute the right hand side. Likewise, if you see the right hand side somewhere, you are free to substitute the left hand side. So, these are called rules of substitution, and they are based on the fact that this underlying formula is a tautology essentially. So, as an exercise that show that this is a tautology. Because all rules of substitutions are based on tautological equivalences essentially. What are the other formulas? You must be familiar with many of them. So, these are known as Demorgan laws. Then even simpler formulas like alpha and beta is equivalent to beta and alpha. Remember that the proof procedure is a syntactic procedure, it just looks at pattern matching essentially. So, if you see alpha and beta somewhere, so for example, we saw rule earlier, if I can find it. Okay. So, for example, we saw this rule which said that the disjunctive syllogism, which says that if alpha or beta and not alpha implies you can infer beta. Remember, this was disjunctive syllogism essentially. But what if you are given beta and alpha and not alpha? Obviously, the pattern matching will not help here, because in some sense this is saying that these two formulas should be matched, whereas these two formulas do not match essentially. Whereas, this kind of a rule, which is as you know, commutativity, which I have written here, alpha and beta is equal to beta and alpha. So, I could have substituted alpha and beta instead of beta or alpha, and then I could have applied the disjunctive syllogism. It allows us to do all these kind of things. And we can also have rules like alpha and gamma or beta is equivalent to alpha and gamma or alpha and beta, which is a well known distributive property essentially. Since we are talking about binary connectives, we may need to use rules like alpha and gamma and beta is equivalent to alpha and gamma and beta, which is a well known associative law essentially. So, with these kind of rules, essentially we can substitute one formula with a equivalent formula, which can be used in other rules essentially. So, what is a proof procedure or proof system? So, remember we had said that is language plus rules. So, I will include both rules of inference and rules of substitution, and you can see that the rule of substitution is equivalent to two rules of inference. You could have broken it down into two rules of inference, where one is the given and the other is the thing that can be added. It is just that it can be done in both ways essentially. So, given a KB, choose an applicable rule. So, let me just write rule of inference, because I just said that a rule of substitution can be broken down into two rules of inference anyway, with matching data. So, I am saying data, but essentially with matching sentences and add the consequent to the KB. So, this thing if I put it into a loop, take a rule of inference, apply it, add something to the knowledge base, take another rule of inference, apply it, add something. So, I have a means of growing the knowledge base essentially. So, at the end of it, if I end up adding some formula alpha to the knowledge base, then we write this notation that the knowledge base, from the knowledge base we can derive alpha. So, let me just add here to yield KB prime. Just to separate the fact that KB is the original knowledge base that you started with, and then if you can apply a succession of rules of inference and produce this formula alpha or add it to the knowledge base, then we say that alpha can be derived from the KB, or alpha can be proved. So, given the KB, we can produce alpha and add it to the knowledge base. We have already seen a notion earlier when we said that given a knowledge base, what else is true, we can determine using the truth table. If so, let me use a different color here. So, if the KB is true, and by this we mean that every sentence in the knowledge base is true and alpha is true, as a result we have already said that alpha is entailed by the KB essentially. We write this as KB entailed alpha. So, a similar symbol, but with two lines here. So, this is entailment. So, essentially we have two ways of looking at alpha. One is through a process of semantics by looking at the truth table and finding out that if my every sentence in my knowledge base is true, is alpha true, then we say that the alpha is entailed by the knowledge base. The other procedure is the procedure that we have just defined here, which is a proof procedure, which says that I can keep applying rules of inference. Now, remember, rules of inference are not part of the language, they are outside the language. That is why we say a proof system is language plus rules of inference. But if I choose a language and if I choose a set of rules of inference, and if by repeated application of rules of inference I can produce a formula alpha, then we say that alpha can be proved in this proof system, or alpha is derivable, or alpha can be derived in proof systems. So, the question obviously we want to ask is, are these two approaches arriving at the same answer or not essentially, because our interest is in truth values, is alpha true or not essentially, but we have started by constructing a machine or a proof system which we will call a machine, which can produce alpha maybe essentially. So, the questions that we had mentioned towards the end of the introductory module was this notions of soundness and completeness essentially. So, just to repeat it quickly, a logic system or a proof system is sound if it only produces true formulas. This procedure will only add an alpha if alpha happens to be true essentially. A logic machine or a proof system is said to be complete if it will add all true formulas. Whenever alpha happens to be true, I can rest assured that my logic machine will produce it at some time essentially. So, if we had such a machine, then obviously we would not have to consider about truth tables and semantics and all this kind of stuff. We could just entrust the task of finding of whether a formula is true or not to the logic machine. If it produces it, we will say it is true. If it does not, then we will say it is false essentially. So, we will look at these notions of soundness and completeness again a little bit in the next class, and we will look at different kinds of algorithms for which can be used to apply the rules of inference essentially. And as I said that there are certain algorithms which are easy to program because there is no guesswork involved, whereas there are other algorithms where guesswork is involved, but you may not be able to write a program to do the kind of a guesswork. So, we will look at 2 or 3 different options, and then we will eventually settle down with 1 or 2 algorithms of proof systems. This exercise is also called theorem proving. So, essentially our task is to design a theorem prover. So, by theorem we mean something which is true essentially. So, we will do that in the next class essentially.